Kinetic Model Builder's protocol window provides an extremely flexible interface for defining arbitrarily complex stimulus protocols with relative ease. So to get started, we have our protocol window selected. We simply do protocol info or simply push the info button in the upper left-hand corner to bring up the dialog of protocol parameters. In the first tab under protocol, we have our sort of general model parameters. We can give it a name, say my protocol. And the next three start, stop, and step parameters define the sample time points used during a simulation. So in this case, we would start at time 0, go to time 1, and our uniform time step would be 1 millisecond. We also have a temperature and a voltage, which are sort of basal conditions applied throughout the simulation. Although these parameters can be changed by adding stimulus pulses, as we'll show in a moment, for temperature and voltage. The reversal voltage is used when computing currents which are due, say, to the flow of ions, where a concentration gradient might also oppose the voltage you apply. So the reversal voltage in this case would be the voltage which exactly counteracts the concentration gradient of your system, and thus the net current would result from a flow of ions that feel a pressure due to voltage as well as a pressure due to a, say, concentration gradient. And at this particular voltage, no ions would flow. For more detail, please see the user's guide. To start equilibrated, this only works for one of the model solvers, the eigensolver, and this simply puts the model into the starting probability amongst all its states, which is the equilibrium probability. And the whether or not current includes gating current is whether or not the current signal also includes the current which is due to the movement of actual model charges, such as those charges defined in transitions. And again, see the user's guide for more detailed definition. The remaining parameters here are all for model optimization, but it's worth pointing out that although the time points are all uniform, rapidly decaying signals, for example, can still be well fit by increasing the weight at the beginning time points versus the end time points, and this will be explained in more detail in another tutorial on model optimization. So once these basic parameters are defined, a stimulus protocol essentially consists of a set of stimuli. So we go to the stimulus tab, and here we have the option to add as many stimuli as we'd like. Let's just add a couple right off the bat. First of all, there are two reserved stimulus names, and those are temperature and voltage. So for any stimuli that are given these names, their values will be assumed to reflect temperature in Kelvin and voltage in millivolts, as defined here in the protocol tab, and they'll be added to the basal temperature and voltage as defined in the previous tab. We can give what other stimuli we want. Typically, stimuli will be used to modulate transition rates by multiplying them by some factor, and this is often useful for ligand binding. So we might want a stimulus which is a drug concentration, and we can just call that drug. Now the units for this stimulus would reflect whatever units we would like as a multiplying factor in our actual model. So if our model transition rates were listed as times drug in, say, molar concentrations, then the values for this drug should represent molar concentrations. If you'd like, you can always simply add the concentration here, although this is now part of the name, and you'd have to refer to this as drug parentheses M, or for molar, instead of simply drug. For now, we'll just keep it simple and just call it drug. So we can give each of these stimuli a pulse, start, duration, and amplitude, and this will define a simple square pulse. So for example, our temperature, we could just start it at 0.3, give it a duration of 0.4, and an amplitude. Let's give it an amplitude of 20, and that'll be 20, which will be added to our basal temperature, which is 298 Kelvin. Let's just give the same pulse durations to our voltage. We can make it slightly shorter, it doesn't matter. Our voltage will give an amplitude of, how about 100 millivolts? And that again will be added to the basal voltage, which is currently 0. And our drug will start at 0.3 seconds, give it 0.4 second duration, and an amplitude of 1, in this case 1 molar. For the moment, we'll ignore the rest of the parameters. Let's close that. So in general, the stimuli, the actual waveforms are not constructed until you run a simulation. However, for visualization purposes, in the protocol menu, you can update, replot the stimuli to only look at the stimulus waveforms versus an entire simulation. So here we have it. A menu for deciding what is displayed in the protocol plot here can be obtained by clicking anywhere on the axes of the plot. So I'll just click over on the axes. Now I have the option to decide what is displayed on the left axis, what's displayed on the right axis, whether or not the x-axis is log scale, and I can also choose to draw lines or symbols. And I can choose the width and size of the symbols. So to make this easier for you to see on your screen, I'll up the line width, and in fact I'll just add symbols as well. We can also export whatever is displayed here to column data or column delimited text file or an SVG vector graphics file. So this is useful for exporting the result of your simulations and for creating figures. Okay, so we're now looking at our drug pulse. And the reason we're only seeing drug and not the voltage or temperature is because in our right axis, we've chosen to select stimuli, which plots all stimuli other than voltage and temperature. And if we want to also look at voltage and temperature, we'd have to select them as well. Since they're on much different scales than our drug, what I'll do is put them not on the right axis, but I'll put them on the left axis, which currently is set to display a bunch of things which have not been simulated and so don't exist. So I'll just select temperature. So now on the left axis here, we see temperature running from roughly 298 or 295. That's what it's set to, temperature 298. Oh no, sorry, this is the drug. Temperature running from 298 up to plus 20, which is what, 318 something. There's our temperature pulse. And in red, we're seeing our drug pulse, and that's utilizing the axes on the right from 0 up to 1. Great. So we could also, instead of looking at our temperature, I'll take that off, we can look at our voltage. So here's our voltage pulse. And our voltage pulse was actually, yes, shown in blue, was actually a bit shorter than our drug pulse. And it's going from 0 up to 100 in millivolts. Okay, so we can also display a whole bunch of aspects of a simulation at the same time in separate plot windows, and that's done with these rows and calls. So here I'll just add a row of plots, and in this first plot we will stop looking at voltage and we'll only look at our drug pulse. And in this second row and plot, we'll look at temperature on the left axis, and we'll look at voltage and not our drug on the right axis, and then we'll up the line width and add symbols to make things easier to see. Okay, so now in the bottom plot we can see our temperature in blue and our voltage in red, and the various axes are shown on either side of the plot. And on the top plot, we're looking simply at our drug stimulus on the right axis from 0 to 1, and there it is. In fact, I'll just put it on the left axis to make it a bit easier to, easier to see. Stimuli on the left axis. Great, there we go. And of course, we can make any number of these plots we want and view anything as many different things as we want at the same time. But I'll just leave it as this to begin with. Okay, so there's our stimulus. We have pulses in temperature, we have changes in voltage, and we have changes in a drug concentration with respect to time. And our model would be simulated to simulate the response to these stimulus conditions. Okay, so a very powerful feature of Kinetic Model Builder is the ability to specify entire families of stimulus conditions with incredible ease. So let's do that now by specifying a whole series of different drug pulses. So we'll go back to our Info tab, go to our stimuli, and if we look at our drug stimulus, if we go to the amplitudes, let's, instead of having this be just a single pulse of amplitude 1 molar, let's make it a range of pulses from 1 to 10 molar. And now let's see what that looks like. We need to update our stimuli in order to visualize it. And now we see actually 10 different stimulus pulses ranging from 1 up to 10 molar. And we're also given a little box here that we can use to step through the various conditions. So we can step through, this has amplitude 1, amplitude 2. They look the same here just because they're all being auto-scaled, but on the axes we can see they're changing, amplitude 3, and so forth. We can get all the way up to 10, and then it cycles back. If we simply delete this, click out, we can see all of the different pulses. We can also specify to look at, say, pulse 1 and pulse 10. Click off to see them. Here's the first and the 10. Or we could even do a range, say, of 1 steps of 3 to 10. There we go. Or any combination thereof, say 1 and 5 to 7. There we go. We can zoom in on the plot anywhere we'd like with the left mouse. The right mouse button auto scales. And clearing that will show all of our parameters. So when a simulation is run, a model's response will actually be simulated to each of these pulses separately. So in essence, instead of running one simulation by having a family of stimulus conditions, we're actually going to run a whole family of simulations. In this case, we'll run 10 simulations, one for each different pulse. And that will all be done automatically for you, which is quite nice. And in a different tutorial, we'll explain how you can summarize a model's response across all these conditions, which is very useful, and even use those summaries to optimize your model. Okay, so let's just go back in here and I'll explain this in a bit more detail because this is a super useful feature. Now let's say that we want to have our drug have a sort of a pre-pulse, which we've defined, which ranges from 1 to 10. And then after we've delivered that, we want to deliver a test pulse, which is always going to be the same amplitude. So this one starts at 0.3, duration is 0.4, so it ends at 0.7 seconds. So we'll start this, say, at 0.8 seconds. We'll just make it 0.1 seconds long. Currently, our protocol is 1 second long in entirety. And we'll give this an amplitude of 10. So this particular stimulus pulse specifies 10 different conditions, and this one specifies 1 different condition. So what happens under the hood is this one condition is padded out to as many conditions are required for the maximum number for this protocol, in this case 10. And it does that by simply copying the very last value as many times as necessary. So this is the values 1, 2, 3, all the way up to 10, and this will simply take on the value of 10 for each of these different conditions. So we can see that now by updating the protocol. There it is. So we have 10 different conditions here and a single pulse to 10 for each one, test pulse here at the end. And if we step through these, we can see what that looks like. Here the first one has duration 1 on the test pulse and, amplitude 1 on the test pulse and amplitude 10, or amplitude 1 on this pre-pulse and amplitude 10 on the test pulse, and so forth as we step through. Okay, so we'll go one step more complicated now by adding another drug pulse. Oh, and as you may have noticed, the fact that we gave this pulse the same name means that all of these pulses will be added together into some final waveform, which we're displaying in the protocol window. So you can add a whole bunch of different pulses to generate very complex stimulus protocols quite easily. So let's make a pulse that starts right away at the beginning. And we'll make that one short as well, just to separate it from the others. And let's give it a series of values that go from 1 to 15. So now we have 15 different conditions. So this 10 will will essentially be the value 10 repeated 15 times. But here we've already specified 10. So the way the remaining 5 conditions are padded out is they take the last value in this list. So here the values will have 1 through 10, and then 10 will be repeated an additional 5 times. And we can see that here. All right. So here's our 1 through 15 pulse, and the 1 through 10, and here's our 10. And if we step through the conditions, we'll see that both of the first two are going to build up until they hit 10, and then only the first one will continue to build under the conditions. Great. All right. So let's remove this pulse, and let's say, for example, we'd like to simulate this entire family of drug pulses in the presence and absence of a pulse of a completely different drug. So we can do that very simply. So let's actually call this drug A, and let's change this first pulse to a different drug. Let's call it drug B, and we'll just give it, say, amplitude 10 is fine. So let's just look at what that looks like. Protocol update plots. Okay, so here's our drug B pulse in red, and here's our family of drug A pulses. And currently, this value of this pulse will be padded out for all these conditions, so it'll be 10 for all of them. And that's exactly what we want. But now we want to repeat the simulation of this entire family with this value as 0. So the way that is done is that we actually specify a matrix of stimulus conditions. And in the case here with colons, and we can also specify this instead of with ranges with colons. We could also specify this as 1, 2, 3 comma separated values. So ranges or comma separated values essentially indicate columns of the matrix of conditions that are simulated, and semicolons separate rows. So now what we can do is specify for our drug B that in one row it has value 0. We separate it with a semicolon, and in the second row it has value 10. So now how this works is that not only are columns padded out to account for all possible conditions, but so are rows. And the way this is done is that in the case of 10, it'll be padded out for all the columns to have value 10, and it'll be padded out where each row is the same as the previous row if it's not specified. So in this case, a row of 10s is copied for another row of 10s to account for the 2 rows specified here. And in this case, we've specified 2 rows but no columns. So each column, in this case 0, is padded out to 10 zeros, and 10 is padded out to 10 10s. And 1 through 10 is now accounts for all the necessary columns, but it's only a single row, so it's copied into another row of 1 through 10. And that row will now correspond to being a simulation with drug B at 0, and then for the second row at drug B at 10. So this will be easier to visualize. So let's update our plots. And now we actually have 2 boxes, in which case we can step through our stimulus condition. The first is the rows, and the second is the columns. So let's simply look at the first row. So now we have 0 value for drug A. This will be red is actually drug B. And that's because the amplitude was 0 as defined there. And we have our entire family of conditions for drug A, and we can step through them using the columns box. There they are. For the second row of conditions, we now have a pulse with amplitude 10 for drug B, but we still have our entire family of column conditions for our drug A, which we can step through as well. So in this case, an entire matrix, in this it'll be a 10 by 2 matrix of stimulus conditions would be computed for 20 total simulations. And you can summarize across all of these as will be described in another tutorial. So this is incredibly useful for generating entire, say, stimulus response curves of your model to some stimuli, and in additionally a 2-dimensional curve where you have 2 different stimuli that are both varying in some condition. All right, so let's come back to our parameters. So it's important to note that you can define sets of values and ranges not just for the amplitude, but essentially for almost any of the pulse parameters. So for example here, let's take our drug B and let's just modulate its start, 0.1 to say 0.05, oops, and we'll end it at say 0.2. So that should give us 3 starting conditions, all of duration 1. So let's just look at that. Protocol, update it. Let's look at the row condition where our plot has non-zero amplitude, and now we see 3 different stimulus conditions. They're overlapped, and we can step through them and see how they sort of move in their starting parameter until we hit the last one, and then once we've hit the last one, that is just repeated for the remainder. Okay, so let's remove a couple of these stimuli, and we'll just stick with a simple drug pulse here. Starts at 0.3, duration 0.4. Let's just give it a one single pulse, amplitude 1, and let's look now at the other parameters. So these 3 define a simple square pulse. If we want to make the pulse a non-simple square pulse, but to have some sort of functional onset and offset, we have got several options. Tau is nice and easy for generating an exponential rise and decay. So we can give this, say, maybe a 0.02 second exponential rise and decay. And let's update that. So now we have our single pulse, but instead of being a square pulse, it rises and decays with the specified time constant. We can optionally specify that exponential rise and decay be sigmoidal in nature. So let's update that. There we go. We have sigmoidal rise, sigmoidal decay. Or we can even input whatever we want for the onset and offset equation. So for example, I might want to input an onset equation, which is a function of the variable t for time. And so this will just be a linear value in time. And an offset equation, let's just make this one exponential to minus t over 0.01. That's great. So the offset will essentially mimic our using a tau, but the onset will be linear. So let's look at that. Here's our linear onset, and here's our exponential offset. And the exponential is starting at the amplitude that is defined by our amplitude parameter, which was 1. Okay, so the ability to specify rows and column conditions actually exist also for these equations. So for example, I could take 2 rows, one where the time is linear and one where, well, we'll keep it linear, but we'll make it twice as fast, 2 times t. And for our offsets, we might have 2 column conditions where the exponential is maybe a bit twice as slow in the second condition as the first. Okay, so let's look at that. Update the plots. I'm only looking at the first row, so let's look at all of them together. Here we go. And we don't need to look at this guy anymore, so I'm just going to get rid of our bottom row. Okay, so we've got drug A for row 1, which is rising with a value linear to t, and under our second row, shown in red, it's rising at still linear, but twice the value of t. And for each of those, the decay, we have 2 decays, which are columns, which are decaying at either 0.01 or 0.02 exponential time constants. So let's look at the first row. Here's our linear onset, and we can step through our offsets, which are our 2 exponential decays. And if we look at our second row, here's our 2 times t onset, and we can step through our offsets. So you can see that you can essentially specify incredibly complex stimuli very easily. And the last thing to note is that we can optionally turn these stimulus pulses, whatever their shape, into pulse trains. So let's just make a simple pulse for this. So we'll have a pulse starting at 0.3. Let's just make it really short in nature, 0.1, amplitude 1. And now let's repeat it 3 times with a period, say 0.2, that'll separate the pulses. And update that plot. So now we have our pulse, 3 pulses in a pulse train. And indeed, of course, these data can also be given as a range of different repetitions, 1, 2, and 3. And updating that, we see all 3 together. But if we step through them, we have 1 on the first condition, 2 on the second, 3 on the third. So I think that about covers it for everything you need to know in building incredibly complex stimulus protocols with incredible ease. Thank you very much.